And by the way, you can see I haven't move camera. That's because right now where the camera is positioned, the field of view of the camera is to here. So if you see me start to write on this side of where it says move the camera and I haven't actually physically moved that, please tell me, because I tend to forget. Okay, but getting back to this, see, there's a correlation between what you learned in base 10 and what you learned, or what you will learn and are going to learn in base 2. Okay. Now another base that's popular, but not as popular as binary in the digital world is octal. Does anyone know what base octal is? Base 8. So how many characters in base 8? 8. And what would the range of those 8 be? 0 through 7, yeah, because again, 0 counts as a character. Often people forget that. They forget that it includes 0. And then your columns in base 8, right? Again, you'd have a radix point. You'd have 8 to the 0, which is how many 1s, 8 to the 1, which is how many 8s, 8 squared, which is what? 64, so how many 64s? And you could keep going, right? And then this would be the 8th column. This would be the 64th column, okay, and so on. Okay. Another base that's used in the digital world, and this one's very popular, is base 16. Does anyone know what we call base 16? Hexadecimal. Yeah, hexadecimal or just hex. So how many characters in base 16? 16. Right? Because again, the number of characters equals the base. Is there anyone that's a Jeopardy fan? You know, the game Jeopardy? Young people, not as popular as it used to be, not as popular with young people. How many people have heard of Jeopardy? Oh, you just don't watch it, but you heard of it. Well, if you watch Jeopardy, sometimes they have a category that's titled stupid answers to stupid questions. And it's because the answer is in the question. So you see, this could be in that category, right? How many characters in base 16? 16, right? The answer is right in the question. Okay, so there's 16 characters in hexadecimal, and for the first 10, we use 0 through 9. Does anyone know what we do next to get the additional characters? Because that's 10, we need 6 more. A through F. Right, A through F. We start using letters. So A is 10, B is 11, C is 12, D is 13, E is 14, and F is 15. Okay, so 16 characters. Okay. All right, so any questions up to this point? Because the next thing to do is to convert between these bases. But before we do conversion, I just want to make sure, does this all make sense? Can you see how it just relates back to what you learned a long time ago about base 10, right? The concepts are all the same. The only thing that's different is the base, right? The base number. Okay, so everybody's good up to this point? Okay, so let's do some conversions. Okay, so the first conversion, we're going to do base 2 to base 10. Okay, so someone give me a base 2 number. Just give me a string of zeros and ones. What do you want me to write here? What do you want to convert? Okay, 0, 1. Let's keep going. Some more bits here. Oh, I didn't tell you this, but in base 10, you know how each number we call a digit? Well, in base 2, each character we call a bit. So this is like bit 0, bit 1. Okay, so what do you want? Give me some more bits here. Okay, 1, 1, and 1. 0, 1. Couple more. 0, 1. 0. How many is that? 2, 4, 6. Okay, that's it. Okay, and we'll put a radix point here, and we'll put like 1, 0. Okay. So to convert this to base 10. Oh, also, just to explicitly identify this as a base 2 number, we'll put a subscript 2, right? Because this could also be like a base 10 number, right? Because you have 0 and 1 in base 10. Right? But just to, explicitly identify that this is base 2, we put this little subscript 2. Okay. Okay, so to convert this to base 10, again, this is our radix point. So just to the left, that's the 2 to the 0. So that's how many 1s, then how many 2s, how many 4s, how many 8s, how many 16s, how many 32s, how many 64s, how many 128s. And then over here, how many halves, how many quarters, how many eighths. Okay, so now wherever there's a 1, that means we have that value for that bit. Wherever there's a 0, that means we don't have that value. So to go from this base 2 number to base 10, we just add up all the values that have a 1. Right? So I take 64 and add 32 and add 16, right? Add 4, add 1, add a half, and add an 8. Right? And you just add them all up. Okay. Now, when I'm doing any writing on the whiteboard during any lecture, if you notice I make a mistake, please tell me. Okay, don't keep it to yourself. Okay, like tell me 15 minutes later, tell me when I make mistakes. I don't purposely make mistakes, but I do make mistakes. Okay, so keep an eye and make sure I'm not making mistakes. So, okay, let's go to add this. So this is going to give us what? 96, then what? 112, 116, 117. And then 5 8s, right? So you could write this as 117.625. And again, you could put a little subscript 10 to explicitly identify that as a base 10 number. So did I do the addition right here? 96 wins, I think I did. 116. Everybody agree? Some people agree. Okay. All right. So no matter what binary number you have, this is the same process, right? You just add up the values where there's a 1. Does anyone want to see another example, or is this good enough? I think on that activity, there's probably a problem like this where you have to go from base 2 to base 10. Everybody's good? Okay, let's go the other way. Let's go from base 10 to base 2. Okay, so somebody give me a base 10 number, not too crazy, like maybe something in the 10,000s. What number do you want to see converted? The questions get tougher as the quarter goes on. I'm throwing you a softball. Here we go. What do you want? Well, let's make it in the thousands. Yeah. Like tens of thousands.
10,400.
Okay, there we go. 10,400 and what?
17.
17. Okay, so we want to take this base 10 number and turn it into binary, base 2. Now, there are different ways to do this. If you had some of this material in a previous at a previous school, you might have learned an algorithm, a certain algorithm to do this. But I'm going to show you how I would do it based on what we've talked about with these columns having certain values. Okay, so what I'm about to show you is not the only way to do it, but it's kind of the way I like to do it. Okay, so you see the way I would convert this to base 2 is I would just start writing out my bit column. Okay, 2 to the 0, how many 1? All right, 2 to the 1, how many 2s? 2 to the 2, how many 4s? 2 to the 3, how many 8s? How many 16s? How many 32s? How many 64s? How many 128s? How many 256s? How many 512s? How many 1024s? How many 2048s? How many 4196s? Let's see, then what's next? We double 4196, that's gonna be what? That's gonna be 8. What did I do? Let's see, did I make a mistake here? Let's see, 1, 2, 4, 8, 16, 33, 64, 178, 256, 512, 1024, 2048. We double this. Oh, it's 4096. See, I made a mistake. Like I said, watch out. Okay, and then if I double this, we're gonna get what, like 8,192? Now, if I double this, I'm gonna get a number greater than the number I'm trying to convert. So you see, that's when I stop. I stop when I get to a value, a bit value that's more than the number that I'm trying to convert. Okay, so I would stop here. Yeah, just to finish this. And 2 to the 2, 2 to the 3, 2 to the 4, 2 to the 5, 2 to the 6, 2 to the 7, 2 to the 8, 2 to the 9, 2 to the 10. 2 to the 11, 2 to the 12, 2 to the 13. Okay, but 2 to the 13, well, 2 to the 13, I would write a 1 because there is an 8192 in this number that I'm converting, 10,417. Okay, so I do have an 8192 in this number, so now I'm going to subtract the 8192 from the 10,417. Okay, so what do we get? We got a 2 here. And let's see, if this was 200, it'd be 217, but it'd be what, 225? Did I do that right? Does everybody agree I did the subtraction right? 10,417 minus 8192. Yeah, 2,225. Okay, good. Thank you for the confirmation. Okay, now this is what I have left over. Well, there's no 4,096s in 2225, so that would be a 0 for that bit. Okay, I do have a 2,048 in 2225, so that would be a 1. And then I subtract that from 2225. So I'll subtract 2048. Let's see, that's going to be 152 plus 25, 77. 177. You agree? Okay, thanks. I don't have 1,024 and 177, so this bit would be a 0. I don't have 512 in 177, so that would be a 0. I don't have 256 in 177, so that would be a 0. I do have a 128. Okay. And then let's see, that's going to be 49, is it? Great. Okay, there's no 64 and 49. There is a 32. Okay, so that leaves 17. So we have a 16. And that just leaves a 1. So these would be zeros. And okay, so 10,417 in base 10 is 101000101100001 in base 2. Okay. Now there is an algorithm that maybe some of you know. Again, if you had like a class like this at a previous school, you know, there's another algorithm where you take the base 10 number and you successively divide it by 2. And if there's a remainder, that means that bit is a 1. If there's no remainder, it means that bit is a 0. Has anyone heard of that algorithm? Yeah, a few people. You know, it's another way to do it. Again, this is just the way I prefer, just because it's based on what we already know. But you know, if you know some other algorithm that will go from base 10 to base 2 and you're comfortable with it, you know, by all means, you can use it. Okay. Okay, so we did base 10 to base 2 and base 2 to base 10. Any questions on Any of these conversions yet? We've got a few more to go here, but any questions up to this point? Okay. Let's see, the next one we're gonna do is base 16 to base 10. Base 16 to base 10. Okay, so somebody give me a 4-character hexadecimal number. So something with 4 hex characters, and make at least some of them letters. Okay, D. Okay, then what? C. C. Yeah. So E, E, F. Okay, we'll do that. So that's our base 16 number. We want to convert it to base 10. And then also let's put a decimal. Let's do like decimal 6. Okay, so we want to take BCEF dot 6, radix 0.6, and convert it to base 10. Okay, well, it's the same idea as when we went from base 2 to base 10, is you just write the value of each of the columns above the characters. So this is 16 to the 0, which is how many ones. This is 16 to 1, how many 16s. This is 16 squared, how many 256s. And then does anyone know what 16 cubed is? Or can somebody do 256 times 16 or do 16 cubed on your calculator? 49. And then this is 16 to the minus 1, so this is how many 16s. Okay, so now we just take what the character is worth, and what is B? What is B in hexadecimal? 11. So you see, we go 11 times 4,096, right? Have to calculate that. Okay, what is C? What number in hex? 12. So then 12 times 256. Okay, what's E? 14. So 14 times 16. And then what's F? 15. 15 times 1. And then we would just take 6 times a 16. All right, so what? This is going to be 40,960 plus 4,096. 40,960 plus 4,000. That's what? 6, 5. So that's 45,056. Is that right? Did I do that right? Do I have agreement or disagreement? You're not going to tell me? You're going to wait till I finish, then tell me it's wrong? That's good. Okay, thank you. All right, then 12 times 256, that's going to be 2560 plus 512, right? 270. That would be 3,072. Okay, then 14 times 16, but that's 160 plus 64. Okay, if you don't agree, slow me down here. Okay, 15 times 1 is 15. I know that's right. And then 6 times 16, so 6 16ths, which is 3 8s, right? All right, then we got to add those all up. So, you know, if we add these two together, what we'll get 48,000 128, I guess. Yeah, and then this would be, we add these, well, add these two together. We get what, 48,352, I think. Is that right? And then this would be 48,367. And then you add the 3 8, so 58,367, 3 8s, which you could write as 48,367.375, right? If you have a base 10 number. Okay, so can you see it's the same thought process as when we went from base 2 to base 16. The only thing that's different is the base, right? Which makes these columns worth different values, but it's the same method, if you will, right? Okay. All right, so any questions about this one? Okay, how about, let's see, we did base 16 to base 10. How about base 10 to base 16? All right, so we go base 10 to base 16. All right, so give me a base 10 number, something again like in the tens of thousands. What do you want to see? It's your choice. $42,000. What'd you say? 581? Yep. Okay, so we want to take that number in base 10 and convert it to hexadecimal. So just like when we were going from base 10 to base 2, I wrote out what the bit values would be. Well, now we just write out what the hexadecimal values would be. So again, we have this radix point. Now we don't have a fraction here, so we're not going to have anything to the right of the radix point. Excuse me. So we just have to worry to the left here. So 16 to the 0, 1 column, 16 to the 1, 16 column, 16 squared, 256, 16 cubed, 4,096. Okay, does anyone know what 16 to the 4th power is? Or can you figure it out, or can you calculate it? Say that again, please. Yes, that is 65,536. That's what the 16 cubed column would be worth. So, see, I can stop here because there's no 65,536s in 42,581. So that would just be a 0. Okay, but now I got to figure out how many 4,096s are in 42,581. So we can figure that out. What would you do? Yeah. All right, just take 42,581. Divided by 4096, and all you care about is the whole number part, right? You're going to get, generally speaking, you're going to get a whole number with some decimal, right? Some decimal portion, but we just want the whole number part. So what do you get when you take 42,581 divided by 4,096? Comes out to what? Anyone do it? Is that 10 point something, right? Yeah. Okay, but we don't care about the points. But yeah, this comes out to 10 point something. So we just care about the 10. So what am I going to write here since there's 10 4,096s in this number? What am I going to write? A, right? Because in hexadecimal, 10 is A. Okay, now I take the 42,581 and I subtract 10 times 4096, which is 4,960. Okay, so let's see, that's going to come out to, let's see, 1581 plus 40. That'd be 15, or what did I say? Well, yeah, 1521. 1621? Yeah, 16. Thank you. Yeah, I told you I make mistakes. Okay, so now how many 256s are in 1621? Six. So you took 1621, divided it by 256, and you get 6 point something. Is that someone, the person that said 60? Are you the person that said 6? Up. I had my back turned. I didn't see it. Okay, so we got 6 256s in 1621. So now we take 1621 and subtract 6 times 256. So that's going to be what? 1536 next. 1536. I was gonna do it out here, but since you did it for me, I appreciate that. All right, so now we subtract this, we're gonna get 85, I think. 85. Okay, so now how many 16s are in 85? 5, right? Because 5 times 16 would be 80. Right? So this would be 5. Then we subtract 80. And then we're left with 5. So that's how many ones we. So 42,581 base 10 is, we wouldn't have to have it as 0. Is A655 in hexadecimal. Okay. So any questions? Because we're about to get crazy. I mean, this is fairly straightforward, but now we're going to do something a little crazy. Yeah, because just like in a base 10 number, right? If you have zeros to the left of the, the most left digit, right? It doesn't affect the value. That's true in any base. If you have 0 left of any non-zero character, right? It's not going to change anything. Okay. All right, so everybody's good up to this point? Okay, the next thing I'm going to show you is I'm going to show you how we can go from base 2 to base 16 or base 16 to base 2 without going through base 10. Okay, there's a quick way, a quick method to go between base 2 and base 16 that you're always using in a class like this, or especially a class like the follow-on class, the CPD 233 class, where you're dealing with a microprocessor that has lots of data, that has lots of bits. Okay, so we're going to do base 2 to base 16. And we're going to do this conversion using what I call grouping bits. The lack of a better name. This is just what I call it. I don't know if there's any official name. All right, so somebody give me a binary number. We want a lot of bits here. So
1 0 0 1 1 1 1 1 1 1.
Okay, keep going.
0 1.
How many is this? 2, 4, 6, 8, 10. Yeah, let's keep going.
1 1 1 1.
Let's be a little
0
different.
0.
Yeah, I might change some of this when I show you what we're going to do here. But okay, how many is that? 2, 4, 6, 8, 10, 12, 14, 16. And we'll add like 2 more over here, and we'll just stay with this. So this is our base 2 number that we want to convert to base 16. Okay, well, what I'm about to show you with this grouping of bits, it's based on that 2 to the 4 is equal to 16. Okay, the key thing being here, the 4. If I take 2 and raise it to the 4th power, I get 16. And we're going from base 2 to base 16. So because of this relationship between 2 and 16, right, the 4th power, what I can do to quickly go from base 2 to base 16, because one way I could do this is I could just go base 2 to base 10 and then go base 10 to base 2, right? Or base 16, right? Basically just do 2 of the conversions that we just did previously, right? But you see, using this grouping of bits, you could do it faster, because what you do in this method is you start with what's called the least significant bit. This bit that has the smallest value, right? This would be the 1s bit. That's called the LSB, which stands for least significant bit. Okay, likewise, this bit over here, right, the one that has the greatest value, the furthest to left, that's called the most significant bit. Okay, so doing this method, grouping the bits, you start with the least significant bit and you group in 4s. And you say, I group these 4 together. Then I group these four together, and because these are identical, I'm gonna change. So it makes it a little different. You'll see why I did that. Okay, and then we group the next four. And then the next four. Okay, now we get to here, and after we group these four here, see how there's only two? But as we just talked about earlier, if you add zeros to the left, and you're not going to change the value. So we would just add 2 zeros here to make this a group of four. Okay? Okay, so you group the bits in fours, and then you write each 4-bit binary group as a hexadecimal character. Okay, so let's start here. We got 1, 1, 1, 0. So this is the ones bit, this is the twos, this is the fours, this is the eights. So 1, 1, 1, 0 in base 2 is what in base 16? E, right? Because 1, 1, 1, 0, that's 14 in base 10, right? Because I have an 8, I have a 4, I have a 2, I don't have a 1. And then 14 in hex is E. So you see 1, 1, 1, 0, that's E. Okay, and now I do the same thing for all these 4-bit groupings. So I come to this 1, 0, 1, 0. Again, this I treat this as the ones column or the ones bit, twos bit, 4 bits, 8 bits. Right, this is worth 1, 2, 4, 8. So 1, 0, 1, 0. How would you write that in hex? It would be what? A. A. And why is it A? Yeah, because 1, 0, 1, 0, I have an 8, I have a 2, that's 10, and 10 in hex is A. You see, this would be A. Okay, now I go to the next 4, I got all ones. So it's going to be F, right? Because this is 15. Okay, then I have 1, 0, 0, 1. 9. Then I have 0, 0, 1, 0. 2. So 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 1, 1, 1, 0, 1, 0, 1, 1, 1, 0. And base 2 is equal to 2, 9, F, A, in hex. And if you don't believe me, if you don't think this is true, we'll take this base 2 number, convert it to base 10, and take this hexadecimal number here and convert it to base 10, and you're going to see it's the same number. Now, I recommend that you actually do that at some point, just so you're convinced that it works. And it's all because 2 to the 4 equals 16. That's why we group it, or group the binary in groups of 4. It comes from this. Okay. And you see why this is very useful is because often in complex digital circuitry, systems like a microprocessor, like the one you're going to build in CP233, which is a follow-on class to this. Well, those microprocessors, they have data that has lots of bits. In fact, the CPE233 microprocessor that you build, it's a 32-bit microprocessor. That means it's dealing with data that's 32 bits. That's 32 zeros and ones. So when you're describing that data in that microprocessor, would you rather say that data as 32 zeros and ones, or would you rather say it as a hexadecimal number? Because if I represent a 32-bit binary piece of data as hexadecimal, how many hexadecimal characters is it going to be? 8, right? Because every 4 bits gives me just 1 hexadecimal character. In fact, that's one of the questions on the activity. Okay, so see the reason why hexadecimal is popular, binary and hexadecimal, those are the 2 most popular bases in digital besides base 10, all right, which you already know. Octal, sometimes you run across it, but it's not as popular as base 2 and base 16. Well, the way to think of base 16, it's sort of like a shorthand for binary, right? Because when you got a lot of bits, you can say it in a lot less. Okay? All right, so do you have any questions up there? Oh, let me ask you one other question. What if we wanted to go from octal, which is base 8, or let's do it this way. What if I wanted to go from base 2 to base 8 by grouping bits?
Group 3 instead of 4.
Right, exactly. You would group the bits in groups of 3 instead of 4. Why?
Because that would equal 7 in decimal. You could have a maximum of 7 in decimal, and that's the range for the possible. It's 0 to 7.
Okay, that's true, but why the grouping of 3?
Oh, because 2 to the 30.
Yeah.
Right?
Yeah, because see, when it's hex, we group in 4s because 2 to the 4, well, octal, right? 2 to the 3 is 8. So yeah, if you wanted to take the same binary number that we converted to base 16, and you wanted to take that same binary number but convert it to base 8, you would just group in 3s, starting with the least significant bit. And then you would write each 3-bit binary as an octal character, which would be 0 through 7, like you said. Yeah. Okay. And you see, this also works the other way. Like, you know, I just showed you binary to hex. You could also go hex to binary using the grouping of the bits in reverse. So hex to binary. You know, let's say we had the hex number A8E2. And I want to go to binary. Well, I can just write each hex character as a 4-bit binary. Right? So I can take this 2 and write it as a 4-bit binary. So what would you write? What's 2 in 4-bit binary? That's 0, 0, 1, 0. Right? With no 8, no 4, you got a 2 and you don't have a 1. Okay, how about E? How would you write E as a 4-bit binary?
1110.
Yeah, 1110, because E is 14. So 1110. How about 8? 1 and then 3 0. Yeah. And how about N? Yeah, 1010 to base. So you see A8E2 hexadecimal is equal to 101010100011100010 in base 2. And see how faster that was than going from 16 to base 10 and then going base 10 to base 2? Because that's the other way you could do it, right? But that would be a longer way to do it. And you're often converting between base 2 and base 16 in digital. You'll be doing it in this class, and you'll be doing it a lot in CP233. Okay. Okay, one last thing, and then we'll stop. You can take a break if you want, and then you can start the activity. And, you know, like I said before, the most important bases other than base 10 in this class, in any digital class also, is base 2 and base 16. But now that you know how to do these conversions, you should be able to convert between any base and base 10. You know, for example, say you were asked to convert, let's see, we'll go 3, 2, 0, 1, radix point 4, base 5 to base 10. You know how to do that? You guys know what we talked about? First of all, is this a valid number in base 5?
Yeah,
Yeah, why?
because all the characters are 0 through 4.
Exactly, right? Because base 5 has 5 characters, 0 through 4. So if you saw something like this, that would be invalid, right? Because there is no 5 in base 5. See, that's a common mistake people make. Because for whatever reason, sometimes people don't think of 0 as a character. Like 0 gets no respect, right? But 0 is a character. You gotta have 0 in any base, because in any base you could have, you know, you could have nothing. All right, so we'll make this easy. I don't know what it was previously, but we'll make it easy. Okay, so how would you go about this? Based on what we talked about, how would you go about converting this to base 10? what we need. Add them up and what are these characters gonna be worth? What's gonna determine their worth? Yeah, it's just 5 to the power, right? So, 5 to the 0, how many ones? For any base, this is gonna be the 0th powers, and this is always gonna be the 1 spot. And then you have 5 to the 1, how many 5s? 5 squared, how many 25s? 5 cubed, how many 125? And this would be how many fifths, right? Because this would be 5 to the -1. How many fifths? Right, so then we just go and add them up like we've been doing. This would be 3 times 125, so that would be what, 375? This would be 2 times 25, so 50. This would be 0. 0. And then this would be 1 times 1. Just 1. And then you'd have 4 times a fifth. 4 fifths. Right, then you just add them up, so you get what, 426.8? Right. Okay, so you see, if you know how to handle all these bases that we talked about that are important in digital, you could do any base. Right? Okay, so I think that's all I wanted to talk about before you start the activity. Do you have any questions before you get started? Okay, like I said, if you want to take a break, that's fine. But now's the time to start working on the activity again. Each table should have enough for the people at that table. If you don't, let me know and I can get you a sheet because I have extras. And then I'll put the answers. I'll put the answers right here. You can come up and take a picture. Don't take the sheet. Just take a picture of it. And if you have questions, by all means, ask. Again, I encourage collaboration, so help each other.
Okay.